very much appreciate Chris to give me such a great time slot right after the fracture energy workshop last week. And I'll try to leave more time at the end for discussions. And today I want to talk about how earthquake arrest could affect its apparent breakdown energy and source time function. And please feel free to interrupt me if you have any question. So in case you missed the workshop last week, I want to quickly define what is fracture energy or breakdown energy. Here I'm taking this linear slip weakening friction, for example, which is a very widely used friction law in earthquake physics community. And this has been presented either as the shear strength as a function of slip on one point on the fault, or as an average shear stress as a function of average slip to showcase the energy partitioning of an entire arrested earthquake, like how I'm showing it here. So the strain energy released from an earthquake rupture can be partitioned into fracture energy and heat or frictional work, and the rest are radiated away. And as you can see, is the green area here. The fracture energy is the energy required to weaken the interface to its residual strength. Until recently, the terminologies fracture energy or breakdown work or breakdown energy has been used sometimes interchangeably. And there are also evidences of secondary weakening mechanisms that will allow the fault to weaken further as slip increases, such as thermal pressurization or off-fault damage. This creates a dilemma to the community for whether to include that pink area, the delta G, into the term fracture energy, as it does associate with the fault weakening. According to the workshop last week, I think I can say that the community can generally agree that the green area should be called fracture energy, and the green plus pink should be called the breakdown work or breakdown energy. Here, I want to make it clear that in this study, we want to discuss the M-member case that does not include secondary weakening mechanisms. In the M-member case without secondary weakening, the estimation of breakdown work should be just the same as fracture energy, as there is no pink area. Because as in the discussion from the workshop last week, Dr. Fiber and Dr. Cameron nicely explained that the rupture propagation and arrest are predominantly controlled by the fracture energy of the initial weakening at the tip of the rupture front, the green area there. Well, at least for very big and fast earthquakes, and which is one of the main conclusion of this recent study. And the fault property that predominantly controls the rupture arrest effectively control how big an earthquake can be. So the green area is what we are going after. But is fracture energy the only controlling factor? Here I want to borrow the cartoon from the elastic rebound theory to explain how an earthquake arrests. Here you can see four states on the location in the faults, and let's say it sits at the residual strength level at the beginning, and then it got loaded and stored strain energy in the surrounding rock. And when an earthquake rupture passes through this location, the previously stored energy are released, and it resumes back to the original state. One important note is that you don't see where the earthquake rupture arrests in this cartoon. This is just one point on the fault that the earthquake rupture passes through. But you can imagine that the location where the earthquake arrests simply looks like the state on the upper right. It sees the rupture front coming in, but it just decided not to rupture and stays locked. So what determines if a rupture front keeps propagating and allows the earthquake to grow larger and larger, or just arrests and concludes magnitude? In the workshop last week, Professor Cameron explained nicely how linear elastic fracture mechanics can be used to predict when a rupture will nucleate, keep propagating, or just arrest. If you are not familiar with the linear elastic fracture mechanics as applied to frictional sliding, please go check out Dr. Cameron's slides through this QR code, or just watch the recording of the workshop on YouTube. Here I simply put that rupture propagates when the energy release rate exceeds fracture energy. Energy release rate is the energy being released if a unit rupture area is increased. And the fracture energy is the energy required to break down the strength of that unit area. Note that the energy release rate concerns the structure and stress distribution of the surrounding material, but the fracture energy is the local property of that uni area that is going to break or not break. So here, let's consider the simplest case where the stress is uniform and the fracture energy is also uniform. What will happen is that a rupture will not stop, will not arrest once it starts to propagate. So to make an earthquake arrest, one option is to have a barrier with high fracture energy so that it can absorb the energy and stop the rupture soon after it propagates into it. And this is what most models assumed, analytical or numerical, but there's no guarantee that this is always the case. There's another obvious option for an earthquake rupture to arrest. It could simply because there's no more energy to release, which can happen if the rupture front reaches a region that is not sufficiently loaded. However, this case is rarely discussed. I can only assume that is because it's too difficult to constrain a non-uniform stress distribution over kilometers of fault lines. But I think everyone can agree that stress distribution is probably not uniform, and it's probably not less variable than material properties along the fault. So please keep this case in mind. I'll circle back to this later. Now, as everyone already know or could have guessed, there's a huge gap between the sizes of most natural earthquakes and laboratory earthquakes. Besides, there's also a huge discrepancy between the length scale of rupture processes. On top of that, experiments with spontaneous rupture propagation show scale invariant rupture processes, but the derived or inferred rupture processes of natural earthquake seems to be highly scale dependent. I was lucky enough to work with Dr. Greg McClaskey at Cornell for my PhD and work on his 3-meter laboratory earthquake apparatus. This experiment is one of the biggest laboratory earthquake and provides us a unique chance to try to bridge the gap in sizes and try to reconcile this discrepancy that the community has not really come to an agreement on. So here I show you the 3-meter earthquake apparatus, consisting of 2 separate granite blocks sitting side by side, and their interface is the simulated fault. They are squeezed by an array of hydraulic cylinders to apply normal stress to the faults, and we use another array of hydraulic cylinders to shear the moving block, applying shear stress along the faults. We install 16 slip sensors and 8 strain gauge rosettes to measure local slip and stresses along the faults. Well, this is actually an old picture. Since then, we have doubled the number of locations of shear strain measurements. So the total number of strain gauge pair is now 16. And the simulated fault has dimension of 3.1 meters times 1/3 of a meter. So why 3 meters? First, I want to introduce H star, which is the critical nucleation length. It's around 1 meter for granite in our lab settings. Let's say a rupture nucleates from the left end. When the nucleation patch extended quasi-statically and its length reaches H star, the rupture starts to accelerate to close to Rayleigh wave speed and propagates dynamically. And finally terminates if it runs out of energy. Therefore, the longer the fault is, the better chance to have a rupture to spontaneously arrest within the fault. Okay, now, before I dive into the details, let's first slow down for a moment and then talk about the big picture here. The one question that we really want to answer is whether the fracture energy is a scale-dependent property that scales over 6 orders of magnitude from laboratory earthquake to big natural earthquakes. Note that we're focusing on the fracture energy, neglecting secondary weakening mechanisms. Here I list 4 different field observations of scale-dependent breakdown energy and talk about which ones we could test with our large-scale lab earthquakes and which ones we couldn't. So first, geological evidence. Even though we do see gouge production after many experiments, we cannot attribute them to individual lab earthquake. Besides, there's no way to separate G and delta G in geological evidence. So this is outside the scope of the study. And second, a slip profile and crack model. From Coe and Schultz, 1992, they see a tail on the slip profile. Oh, sorry, what happened? Okay, back. A tail on the slip profile, and it spans about 20% of the overall rupture length. They call this region the friction breakdown zone. and propose a bell-shaped model, as the slip profile looks like a bell. As we do have rupture that arrests within the fault in our experiments, this is something that we can test. Okay. And there is seismological estimation. The ingenious G prime that is so elegant and simple, but since our experiment does not produce earthquake rupture that spans orders of magnitude, we can only take what we learned from the lab and scale it up with numerical simulations, then analyze them with seismological methods. So yes, we also tested this method. Finally, there is kinematic version. Since the literature only use up to about 1 Hertz of sampling frequency, and there is also spatial temporal smoothing, we just don't think that the relevant process that we're looking for is resolvable, which is usually at micron level. If you're recording an earthquake with slip rate of 1 meter per second at 1 Hertz, the fault slips 1 meter between 2 data points. And that is the length scale that we would consider secondary weakening mechanism has already kicked in. Hence, we decided not to attempt to test this method from our perspective. Okay, so now let's talk about the breakdown energy estimated from slip profile with crack models. When we look at the mechanical behavior of frictional slip, the shear stress drops down within the area that has slipped. And under this context, slip profile and stress changes are mechanically linked. Here we first define the slip profile as the spatial distribution of relative on-fault displacement of an earthquake rupture, something like this. And the stress change is the on-fault static shear stress difference between before and after the rupture. And the constitutive relation between slip profile and stress changes were derived by Belby and Eshelby back in 1968. Let's call this equation 1. And with this, we can calculate the associated stress change solely from the first derivative of the slip profile and elastic moduli, assuming the median surrounding the fault remains linear elastic, as shown in the case with this basic elliptical slip profile here. And here I'm showing you the measured slip profile and static stress change distribution of 2 typical types of rupture events in our experiments, the completely contained and partially contained. You can see the stress change doesn't just jump directly from minimum to maximum. They smoothly transition across multiple measurement locations. And another important note is that our slip profile measurements also show roughly linear taper at the edge of the rupture, similar to field observations. This somewhat hints the friction breakdown zone from Cohen and Schultz 1992 and Schultz and Lawler 2004. And I'll get back to the implication of this feature later. As I mentioned earlier, the constitutive relation relies on the first derivative of the slip profile, which is probably not accessible with this sparse array of slip sensors that we have. So to facilitate further discussions, we've proposed an analytical model to constrain the slip profile and the associated stress change distribution that we measured. But I'll not go into a detail today, so please refer to our paper if you're interested in details. Now, we fitted the proposed model to our experimental measurements for 24 completely contained ruptures and 13 partially contained ruptures. The spatial resolution of slip profile measurement is arguably not high enough to resolve the fine detail near the rupture tips. However, according to equation 1, stress change is very sensitive to the details of slip profile non-locally. Therefore, simultaneously fitting measurements of both slip profile and stress change distribution provide better constraint for the fine details near the rupture tips. And for the 2 ruptures on the right here, I'm comparing our proposed crack model with elliptical model and the bell-shaped model. And you can see that our proposed model fits so much better because we allow the stress change to gradually transition from minimum to maximum. Okay, now, before moving on, we want to define a new terminology, the earthquake arrest zone. It is a subsection of an earthquake's rupture area. It is bounded on one side by the tip of an arrested earthquake rupture. And the boundary on the other side is not as clearly defined, but it's roughly located where stress changes start to increase. Note that is the delta tau, not tau. If we plot it in the stress changes versus slip domain, it appears to be similar to slip weakening friction. Now you might want to ask, how is this different from the friction breakdown zone that Corey and Schultz 1992 proposed? Well, both this friction breakdown zone and slip weakening friction are defined on the absolute stress, not stress changes. And later studies took the slip weakening friction as the foundation and derived process zone, breakdown zone, or cohesive zone in these studies with very similar concept. The width of the cohesive zone can be derived in the context of fracture mechanics, and this is the equation. But one very important note is that all these zones are based on the absolute stress instead of stress changes. So the big question here is whether the cohesive zone and the arrest zone are related in any way. Because if they are related, then we can probe into the friction law and fracture energy, of course, for this interface by just the measurement of slip profile. And that's what the previous studies tried to do. Now, putting earthquake arrest zone and cohesive zone side by side. In our experiments, the width of the arrest zone, WAZ here, is about 20 times larger than the cohesive zone estimated from spontaneous dynamic rupture propagation. Also, the WAZ is about 20% of the overall rupture length, which is somehow consistent with field observation, and it means that it depends on the rupture size. On the other hand, cohesive zone should be a local quantity and should not depend on the overall rupture length. Finally, because
Chun,
yes.
Sorry, can I ask you a question because I misunderstood, I got lost,
yes,
my
sure.
fault, sorry. When you discuss about the earthquake arrest zone,
yes.
you are referring to the termination of the rupture of the whole fault plane, not the healing of slip in an individual point in the fault during rupture.
Yes, I'm looking at the spatial distribution. So just like what I have here. So you can see the x-axis here is location. So this is the entire, for example, this is the entire rupture area.
Okay, so it means that the rupture is stopped.
Yes, has already stopped.
Okay, thanks.
Yes, thank you. Right here, okay. Yeah, and finally, because this fracture energy is simply the shaded area in this absolute stress, so tau versus delta, the slip relation, Cohen and Schultz 1992 directly plotted the stress change versus slip and defined the area under this curve, the earthquake fracture energy, EG, and assume it's properly representing the true fracture energy. And what they are doing is actually assuming that the initial stress distribution is uniform. So the difference between these two curves is only an offset and it doesn't affect the area. But that might not be correct because according to fracture mechanics, under uniform initial stress, a rupture will never stop once nucleated, unless it's a huge barrier with very high fracture energy. I'm not going to detail here, but if we impose all the field observations as constraints, we arrive at the same conclusion as Cohen and Schultz. The fracture energy scales linearly with the size of a rupture. However, we're quite certain that the fracture energy of the ruptures in our experiments are more or less constant through analyzing their dynamic propagation. So looking at these conflicting evidence, we suggest that the earthquake arrest zone is actually reflecting the heterogeneous initial stress distribution, which has not been brought up in this context before. And the size of the arrest zone depends on how far the rupture propagates into unfavored stress condition. In other words, it's not the increased fracture energy that stopped the rupture. It's the unfavored stress condition that stopped the rupture. If you're interested in the details, please go check out our 2018 paper where we analyze rupture arrest using linear elastic fracture mechanics. And you can see here that the blue dashed line here is the fracture energy, and it's more or less constant. While the orange curve here is the energy release rate. It drops drastically when reaching to regions with initial stress lower than residual strength. Okay. To demonstrate our idea, we set up a 2D numerical simulation with slip weakening friction, as shown in the figure on the right, which brings in a constant fracture energy throughout the whole domain. And we impose a plateau-shaped initial stress distribution shown below, where the purple and red dotted line indicates the level of peak strength and residual strength, respectively. The rupture was nucleated by a C crack extending 10% of Rayleigh wave speed right at the center of the stress plateau. after the length of this C crack exceeds the critical nucleation length at the H star, its propagation speed is expected to spontaneously accelerate to close to Rayleigh wave speed, and then slow down and stop after propagating a certain distance into a region that has initial stress lower than the residual strength. Here, I'm going to show you how the simulation went down while simultaneously plotting the spatial distribution of slip, stress changes, and absolute stress, and also stress changes and absolute stress plotting against the slip. Okay. In the spatial distribution of stress changes, you can see that the actual cohesive zone, these spikes, are tiny compared to the arrest zone. So this huge ramp here. And that tiny feature is very likely to be missed from field measurements or in large-scale experiments. While in the stress change versus slip domain, it shows an apparently large and growing slip weakening feature. In absolute stress versus slip domain, you'll only see the true slip weakening relation that we impose in the model. This example clearly shows that the fracture energy estimated from a crack model is not representing the true friction law anyway, because the crack model can only give you the stress change, not the absolute stress. Again, it only reflects the heterogeneity in initial stress distribution. If you're still not convinced, let's take a look at another example just for fun. We remove the gradual transition in the initial stress distribution. And so now the initial stress is a boxcar. And the resultant rupture looks very similar to the bell-shaped model proposed in Covey and Schultz 1992 in both slip profile and stress changes, except the fact that we actually see the cohesive zone that is very likely to be missed in sparse measurement locations in experiments or on natural faults, especially if the rupture is not just 1 meter wide like this, but kilometers wide. So the key factor that the previous study missed is very obvious now. If you only look at the difference between two states, you cannot get the information of the absolute stress without knowing the absolute stress field of the previous state. Therefore, you cannot use that to estimate the friction law or the fracture energy. Okay, in the previous section, we concluded that the scaling of fracture energy derived from crack model is not representable if you consider non-uniform initial stress distribution. However, the scaling is also observed in the seismologically estimated fracture energy. So we decided to revisit and examine the seismological approach by using a suite of scaling numerical models that share identical friction law, fracture energy, even element size and time step. Then extract these source parameters from the model and see if the seismological approach gives us the imposed constant fracture energy or the same scaling that's seen in the natural earthquakes. Okay, here I'm showing you the same energy partitioning that I showed at the very beginning. So the idea that Abercrombie and Rice came up was very clever. Assuming that this graph is correct, then G bar can be isolated simply by rearranging these terms. And G prime here is the resultant formula that Abercrombie and Rice 2005 derived to estimate fracture energy through seismic source parameters. So the stress drop here, delta tau, can be estimated by Broom's model, which depends on M0, the low frequency amplitude of the source spectrum, and the radius, source radius, which can be estimated through the corner frequency of the source spectrum. And mu is the shear modulus of the surrounding material, and the radius, radiated energy can be estimated through the integration of this velocity spectrum. And the average slip can be calculated from M0 and A is the rupture area, which is assumed to be circular, therefore pi r squared. And there you go, seismologically estimated fracture energy. Actually, Dr. Abercrombie gave a very nice and detailed talk regarding this method last week in the workshop. So please go watch the recording on YouTube if you missed it. Anyway, the idea is that if all parts shown here are estimated accurate enough and all the assumptions are valid, I have no doubt that this formula will give you the average breakdown energy. The problem is, We also know that assumptions in seismological methods of all these components are not always satisfied. So we want to ask, will G prime scale even when G is constant? Note that we want to test the case that there is no secondary weakening. So even the breakdown work is constant in our simulations. Inspired by the earthquake rest zone model I showed you from the previous section, we extended it to a 3D problem. So now the initial stress distribution is an axisymmetric plateau on a 2D fault surface. And the stress at the plateau is higher than the residual strength and drops down linearly outside the radius of A. And the rupture is then expected to arrest somewhere. The initial stress is lower than the residual strength, just like before. And all models share identical friction law, and therefore identical fracture energy. We then consider two different end-member scaling cases. The scaling case A has self-similar initial stress distribution that we picked to match the 20% arrest zone observed by Cohen, Schultz 1992, and Schultz and Lawler 2004. We use Greek alphabet chi as the scaling factor. The dashed black line on top panel here is the initial stress, and the purple and red dotted line indicates the level of peak strength and the residual strength, respectively. As you can see, the initial stress looks identical in different scales, while the space is 32 times wider on the right. And the resultant stress change profile and slip profile are also nearly self-similar, as we expected. In the scaling case B, we keep beta constant. In other words, rupture at different scales are stopped by basically the same stress barrier. And this is very similar to the boxcar example from the last section, but slightly more gradual. The most obvious difference is to scaling case A is that the rupture is no longer self-similar. We ran simulations in these two scaling cases for chi from 1/4 to 16, spanning almost 2 orders of magnitude. Note that the only difference between all these simulations is the initial stress distribution. The two scaling cases closely bound the general understanding of earthquake source scaling relations, as shown by the black dash line here. So I'll just skip ahead here. Please refer to a manuscript for details. So now we have confirmed that the scaling models are obeying established understandings on earthquake scaling. Let's take a look at G prime. Just as we suspected, G prime is scaling, despite the fact that we impose the same constant G in all models, and there's no secondary weakening whatsoever. So what happened? Here I'm showing you the stress distribution during the simulation in both cases for chi equals to 4. Okay. So as I take a closer look at the simulation result, I noticed that the stress inside the rupture area drops a little more after the rupture front is arrested in both cases. So let's take a closer look from the cross section. We can tell from the peak in here and there that the rupture arrests around the time between maybe green and yellow. And then we look at this tau minus tau r, we can tell that the stress drop a little more after that timing, after the green and yellow. So they are all orange and red. And for scaling case B, which arrested more abruptly, we see a bigger stress drop after rupture arrested and more complex behavior. This is called the stress overshoot. It happens when the rupture front arrests, but the interior part of the rupture area didn't know that it needs to stop yet. So they slip a little too much and release some strain energy that they shouldn't have. Therefore, left the final stress slightly lower than the residual strength once everything is settled down. This is a widely observed mechanical behavior for crack-like ruptures. And on the other hand, if the rupture is pulse-like, there will be a stress undershoot, meaning that the stress increases when the rupture arrests. So what will be different if the stress drops a little more upon termination? In fact, there is an assumption in G prime that becomes invalid. G prime assumes that the final stress equals to the residual strength. Therefore, in the case of stress overshoot, G prime overestimates G by this blue rectangular area that we call overshoot energy. The same as previous studies, we found that the average stress overshoot is basically constant across all scale of our models, and it's about 10 to 20% of the stress drop. And that explains why we're seeing G prime scaling as D to a power of roughly 1 at larger chi, because G prime is being dominated by this second term here. Likewise, if the final stress is higher than the residual strength, which is the case of stress undershoot, then G prime will be underestimating G because the second term will be negative. And that brings up something that's rarely discussed. Abercrombie and Rice 2005 actually reported that there are about 1/3 of the earthquake they studied resulting negative G prime. And they seem to evenly distribute across magnitudes. So perhaps those earthquakes have pulse-like, are pulse-like and has stress undershoot. And here is our result plotting on top of Abercrombie and Rice 2005 and parallel 2020. You can see that the constant overshoot of 1 MPa, the dotted line at the center, fits our scaling case A very accurately. And it's not very far from scaling case B where rupture arrests more abruptly and has higher stress overshoot. And almost all the data points are bounded between the curves from 0.1 to 10 MPa overshoot. Evidently, one does not need a complicated simulation with enhanced dynamic weakening to match the seismological observation, by parallel 2020 results here. The value of G prime is more likely being dominated by the overshoot energy rather than the actual fracture energy. Therefore, it is possible that G is not a scale-dependent property. It can be a small number that is being overshadowed by overshoot energy. Just a tiny bit of stress overshoot can make G prime scale. And now here, I want to show you an additional way to compare numerical simulations to natural earthquakes using the source time function. The source time function is the moment rate as a function of time. It is one of the most direct measurement of earthquakes, and it contains information of how an earthquake grows and arrests. Here I'm showing you the source time function of all the simulations. You can clearly see that the growth phase of all simulations are identical before reaching unfavored stress condition. And the scaling case A arrests more smoothly and gradually than scaling case B. When comparing to Dinot 2019, we found that some natural earthquakes do share the same feature as this quadratic growth phase. And but some natural earthquakes like in Mir et al. 2017 have linear growing phase here, as you can see. And in addition, even though the scaling case A is its gradual arrest is reasonable fit to observations, all our models seem to exhibit rapid post-peak decay and slightly positive skew, meaning that it's leaning toward right. And this implies that our simulated earthquake do not arrest slowly enough, or that slip ceases too quickly after the rupture initially begins to arrest, which of course can be fixed by tuning the slope of the initial stress or even adding secondary weakening mechanisms. But that kind of tweaking is more suitable for studies on specific earthquakes. Here we want to focus on more general behaviors, such as how will you get a linear growth phase? Some intuitive or an educated guess might be, oh, it's propagating laterally like an earthquake rupture that saturates the entire seismogenic depth. But we found that we don't even need to change our model that much to get a linear growth phase. In this case here, we simply take the model in scaling case A and move the nucleation location to the edge of the stress plateau, shown on the right. Okay, now I'm playing an animation. As you can see, the rupture is simultaneously growing and arresting on the case of edge nucleation. Well, maybe we should watch that again. And the resultant rupture are basically the same. The difference is minor. And the pink curve here is the source time function of the edge nucleation simulation. It's surprising by only moving the nucleation location, we effectively get an earthquake with linear growth phase. This highlights the fact that seismological methods are measuring average response over the entire rupture area. and we must be very careful when interpreting what we're seeing. Oh, wow, I went over all the slides very quickly. Okay, in conclusion, instead of having a list here, I'm just going to put these two down. Fracture energy could be scale invariant and still exhibiting these field observations that are used to claim otherwise. And non-uniform initial stress distribution matters. I agree completely with the community that fracture energy or breakdown energy is important. But remember, it is a property that is meant to be used to compare with energy release rate, which depends heavily on initial stress distribution. But the studies we have done so far as a community is disproportionately focusing on the fracture energy alone, neglecting the possibility that non-uniform initial stress distribution could easily explain a number of field observations, as I try to demonstrate here in this talk. I'm not saying that our model is more correct, even though the earthquake red zone model seems to match field observations reasonably well. I just want to say that these very simple model that explains what happened in our lab are also capable of explaining field observation that previously required complicated model to explain, simply by introducing a very simple shape in initial stress distribution. That is, of course, not going to be 100% correct. And I hope this could help reconcile some discrepancy between length scales and eventually make more robust links between laboratory experiments, natural earthquakes, and numerical simulations. And thank you for your attention.
Okay, fabulous talk, Chun. I'll ask everyone to unmute and join me in thanking Huey for a great talk. Yeah, well, we especially encourage young people to, early career scientists, to ask questions. Raise your hand with the reactions feature of Zoom, and we can have a combination of questions and discussion led by Chun. Bin Hao, please.
Great talk, Chun. Thank you very much.
Thank you.
I'm particularly interested in the last case that you showed, the edge nucleation. Could you remind me what's the difference, like the setting of these two simulations?
Oh, yes. Okay. So here I'm showing you the absolute stress. So this is a stress plateau. So what I did to this is just moving this nucleation location. You can see the star here from the center of this stress plateau to the edge of the stress plateau. Mm-hmm. And that's all I did.
Oh,
and yeah, that's all the difference. And you can see that the resultant rupture are basically the same. Oh, actually, I have the final distribution here. I put it here. As you can see, of course, the overshoot looks a little different and it's a little lopsided, but overall, they are pretty much the same.
And both of these are crack-like ruptures?
Yes, both these are crack-like.
Interesting.
Yes. And the resultant source time function are very different. Yeah.
Thank you.
Thank you.
Franta, please.
Hello. Thank you. Very nice talk. I'm curious, being a modeler of earthquakes and doing dynamic slip inversions. I'm interested in the rupture velocities that are coming from your simulations, because what at least from my experience, and I think Alyssa also mentioned this during the workshop, that for our modeling we need a large DC, or at least DC that seems to scale with the size, with the magnitude, because we need for magnitude 6 we need DC of the order of 0.5 meters, let's say, even few meters close to the surface. And because we need to limit the rupture speed at around, I don't know, 2 kilometers per second, 2.5 kilometers per second, clearly below the limiting speed that I think you would reach easily when assuming a small DC or small fracture energy. So I'm curious about what are the rupture velocities in your simulations.
Yes.
Yeah.
Yes. I don't have the exact number on top of my head, but I'm sure that they are sub-Rayleigh. So they're definitely below Rayleigh wave speed. And during the setup of models, I do encounter some super shear. And I found that there are two key factors that are very important to avoid super shear. The first is how you set up your C crack. If you let your C crack to grow too fast, say maybe just 50% of Rayleigh wave speed, that could impose a lot of energy into your model and make it go super shear. So that's why I only let the C crack to grow at 10% of Rayleigh wave speed. And the second thing is the stress level. The initial stress cannot be too high compared to the residual stress. I think there's Andrew's paper that discussed this S factor.
Yeah.
So you can, so that has to be low enough to avoid super shearing. But the one thing that was particularly important for me was the rupture velocity of the C crack. It has to be slow enough. It will waste a lot of time during the nucleation, but that's worth it. Hope that answers your question.
Yes. Thank you.
Thank you.
Meng Li, please.
Yeah, hi, this is Meng.
Hi.
I have two questions actually. One is like following Binghao's question in the last results when you compare the nucleation at the center and the side. I know this is like an artificial nucleation, but usually, let's say like if you have a ratio between your domain size and your H star, the nucleation size, then if the domain size is large enough, then it prefers a edge nucleation rather than a center nucleation. And how do you like combine that in your case, or how do you like explain your edge nucleation from that perspective of view? And another question is that you use a sleep weakening law here, and what if you are using something like a rate and state where the GC may not really defined to be fixed, even if you are using the same rock property, and how will that change your result?
Yes. Okay. So the first question, you're saying that if you have a domain size that is larger than H, a lot larger than H star, is going to prefer to nucleate at the edge of the stress. Okay. Well, I can't answer that question because here is just purely artificial. So I just comparing these two cases, but I guess you can make a more rigorous study on that, of course. And for the second question of why we're choosing this linear slip weakening and what would be different if we use rate and state, as you can see from here, or maybe I should just pull out this. You can see that for small and big earthquake ruptures in our simulation, or sorry, I should just get back to this. The H star is pretty small, and after that, actually the rupture propagation velocity just converges to just some number below Rayleigh wave speed. And even though rate and state friction has fracture energy depending on the rupture velocity, if you have a steady propagating rupture, then it's basically very similar to a slip weakening model. So for our setup here, the reason why we have a plateau, have a flat surface here, is just to enable the rupture to go steady, go into a steady rupture propagation. So I think, even though I haven't tried it, but I think with this steady case that we have like this, using linear slip weakening law and rate and state friction will not give us too much of a difference. That's just my guess here. Yeah.
Thank you.
Thank you.
Massimo.
Yeah, thank you very much. It's a very nice talk, interesting and stimulating. So I have two questions and one comment. The first question is the slip amplitudes, because you are modeling amplitudes of 40, 50 microns, and you get a stress drop of 2 megapascal. How do you think that this is a scalable, a real earthquake which has much larger amplitudes with not bigger stress drops?
Actually, the stress drop we have is about, I think it's 6 MPa. in these simulations. Yeah,
so you have a difference in sleep of more than 4 decades with a difference in stress of 1 decade. So how much do you think that when you discuss the arrest of sleep pools with microns amplitudes or tens of microns can be scaled to an earthquake with a meter of sleep propagating 3 kilometers per second?
Yeah, so that's the reason why we draw these lines here, because we think that, okay, all the big earthquake simulation that we have is basically having the same behavior, so we stop running them, because then we might need maybe thousands of terabytes of memory to run the bigger ones. And so here I'm just saying that if you have a constant overshoot, stress overshoot, then you can estimate that, let's just say it is 0.1 MPa, but we have a bigger and bigger slip, average slip distance. With this, you can still be scaling very far above the G that you could potentially have. So we're scaling this results in this perspective from this equation here. But I'll say that, yeah, of course, the simulated earthquakes that we have are on the lower side of comparing to all the earthquakes. Yeah, I hope this answers your question.
To actually, with this explanation, you introduced my second question, which is the idea of the partitioning between scale invariant fracture energy versus scale-dependent fracture energy. It is mostly proposed in theoretical models like yours, or in experiments in which we have a very peculiar fault zone structure, like large experiments with bare surface, PPMI, polymer, other types. So these are experiments in which the strain is completely localized, and therefore everything is imposed to be at the tip, which is not always what we observe in nature for a realistic fault zone. At least, even if I have a localized principal slipping zone within a gauge, I have the gauge material and the shear fabric evolution that at least might represent an energy sink. So do you think that this idea of the partitioning, it is somehow model dependent of lab setup dependent?
I can only speak from the result of our experiment. So I'm not saying that it's fracture energy is definitely not going to scale. I'm just saying that maybe we don't have as much of evidence that fracture energy is scaling, because apparently this G prime can scale even when G is constant. So I'm just throwing out a question of, okay, so in our setup, we have constant G, but we still see scaling G prime. So what is the evidence, except for those secondary weakening mechanism that is going to tell us that, the initial edge localized fracture energy is scaling. I think that's more of what we're trying to tell here.
And my comment, it is important to me because I think that it is coming of course, after the workshop. So you knew the risk that you had with this seminar today after the TRIS workshop. However, I think that there is a misunderstanding about the interpretation, what we call breakdown work, okay? So we can define breakdown energy as we wish on this model-dependent picture for a point source. But by definition, breakdown work is the integral below the slip versus, the shear stress versus slip curve over a minimum level of traction. Mm-hmm. So the breakdown work, it contains anything that is dissipated on the fault zone. And the interpretation of the breakdown work strongly depends on the way in which shear stress evolves with slip. So I disagree in putting the breakdown work as a portion of this picture, because the breakdown work, by definition, it is the integral of everything, including the green. So the breakdown work is the integral of the stress integrated versus slip. So How it is partitioned, it is another question, but we should remind that the breakdown work, it could be macroscopic, as it could be not measurable, it could be even less, but in my opinion, we should at least try to, as David was saying, agree on the terminology. So the breakdown work is the integral of the whole stress evolution. If the stress is evolving like ANIDA sleep weakening law, or like a continuum decrease of stress with sleep, this will make the difference in the interpretation of the energy, including your results. But I will strongly encourage everyone of calling breakdown work as the integral.
Okay. Yes. Huey, yeah, please respond, and then I would like to come back to the talk, and we can go back into the workshop mode, let's say, in a minute. But,
yes.
Huey, do you want to respond directly to that right now?
Yeah, I agree that the breakdown work should be including all the processes there, because I think that's why we have a different name. And fracture energy should be just the screen area, because that comes from the fracture mechanics. So I totally agree. Yeah.
Okay, yeah. Sumaya, please.
Hi, thank you for your talk. I was wondering where exactly is the overshoot coming from in your simulation? As if I understand correctly, you apply a sleep weakening friction law, so the stress should be limited at the residual stress. So at what point in the simulation does it goes out of this friction law and the overshoot happens?
Yes, this is a very good question. And here, that brings up a very important point, is that friction law, so that the stress does not necessarily going to follow the friction law, because a fault can be weakened, right? So it can be unloaded. When the fault is locked, the stress can be as low as 0, and it's not, as long as it's not slipping, right? So what happened is that, okay, if I have the plot here, so you can see that stress, just those stress are dropping down after the fault is locked. So it's being unloaded because it slipped too much, and it's readjusting all the stress distribution. So what happened is, if they, you can consider this, I have a probably bad analogy, as if you're driving in a traffic and suddenly there's a car in front of you stopped, and every car behind him has to stop. And if they are not stopping, quickly enough, they are going to smash into the car in front of you. So that's very similar to what happened here. They just drive too far away than what they should have. So they release too much strain energy, and that has to come from something. And that is being materialized by drop in stress.
So at this point in the simulation, the stress is not described by the friction law, but by the fault is locked, actually. Is that what you say?
Yes.
Okay, and so it's just the elastic behavior that
yes.
plays the role.
Yes, okay. Because all the points only have to follow the friction law when it's slipping, okay. Under this slip.
And thus you have a healing criterion, like when the slips, the velocity, the slip velocity go to 0, you relock the fault or something like that in the simulation.
No, we don't put that into this. So that is purely elastic response. Okay. But of course, you can add that into the simulation, and then you'll probably get pulse-like rupture if you have a strong healing.
Okay, thank you.
Thank you.
Yeah, thanks. And as we go to Georg, I'll further encourage everyone, and especially early career people, to raise their hand and ask a question. Georg.
Sir, you're muted.
Great talk, Chun.
Thank you.
I very much enjoyed it. Very sort of didactically well prepared. Now, I still have a question. So when, I understand that there is this attempt to separate the fracture energy being a material constant from whatever is left there. Now, the fracture energy, when we measure it for a given set of thermodynamic conditions, is a very small value, right? You would agree? It's of the order of a few joule per square meter. Mm-hmm. So that's noise if you compare it to the energy that is commonly, assumed to be fracture energy or breakdown energy, which is somewhere between 10 to the 4, 10 to the 6 joule per square meter, right?
Mm-hmm. Yes.
So there's really no hope from that kind of data to deduce these small numbers, okay? So it's kind of an academic exercise, excuse me if I say that, to say, okay, I appreciate the idea that for a given set of thermodynamic conditions, I have a constant value that characterizes, let's say, the breaking of bonds or something like in an Obrymov experiment. I assume that to be a constant value, but I deal with much larger numbers. So then the question really is, what causes these larger numbers, right? And there I go back to Scholz, where, you have this ratio of what he calls this taper, constant taper or whatever, that more or less characterizes a critical strain, right, for the material. So maybe we are dealing with something that is better defined in that kind of a theoretical, in that kind of a framework. Because this number doesn't really, when Jim Rice, when Palmer and Rice created their, their model, they probably didn't.
The FTT,
Yeah. They probably didn't think about this. Okay, and what makes me particularly skeptical also in this context is when we try to extrapolate, even in the lab, the numbers that we measure. So if I go from the fracture energy of a tensile fracture that I measure in Obrymov type experiment, I go to an ISRM, I mentioned this before, chevron notch test. I jump from a joule per square meter to 100 joule per square meter. Okay, and the reason for that is because of the complexity of the tortuous fracture paths that go through this chevron notch test, which involves both tensile fracturing and shearing, and all sorts of other things. So I wonder if we shouldn't, go back and maybe, I'm not sure if I interpret Massimo correctly there, but assume that we have something that we should not call fracture energy anymore. Yeah, to 99.9% for the case of earthquakes.
I also have a question on this topic, because if, let's assume this secondary weakening is very minor, then the boundary between this pink and orange energy are just getting blurrier and blurrier. So if the delta G is important, then I would say that maybe the frictional work is not less important in this context.
Yeah. So that was sort of a question and a comment, and I don't really know what I was rambling around, but I find it fortuitous to try to, to discriminate these things. It's of course worth effort doing that, but I, given the relationships, maybe not worth the effort.
Yeah, interesting point. Let's see what Bin Hao has to say, and then we can, I see Massimo's got his hand raised. If you don't mind, Chun Yu, we can, have a general discussion. Okay, partially.
Yes.
I don't feel like you need to. I hope you don't feel like you need to answer every one of these questions in discussion. Right? We can bring other people into. Bin Hao, please.
Thank you. Could you get back to the figure that you referred to before, like the edge mutation? I want to see the sleep snapshots again. The sleep shot evolution that you show. These are both crack-like ruptures. The thing that confuses me now is that if both of these are crack-like ruptures and they have similar like growing process, how can they be different in the source time functions that grows?
Okay. I want to just play this animation once again. And you can see from the right that it's arresting while it's still growing. So on the right side is arresting all the time, but at the same time it's also growing. So it's a competition between growing and resting. And what happened is that they kind of cancel out in this simple example, and they just looks like a linear growing phase. But if you look at the very beginning, it's still a pretty a quadratic growth. But after they are starting to cancel each other, arresting and growing simultaneously, that behavior cancels out. That's why you're seeing, as an average response, they looks linear. So of course, it's still growing in the same way. It's just that if you average them all together, it happens to look like this.
Okay, thank you.
Yeah, thank you.
Yeah, Huey, really great talk. I wanted to just chime in with a kind of a quick point of clarification, I guess. You made a really nice point about the difference between the role of, let's say, initial stress versus the possibility that fracture energy is going to itself, be drastically different along the fault. But I wasn't quite clear. Like, did you decide not to mess around with that too much in your models? Or did you think it was worth running? Do you think it's worth running more models with more complex initial stress states to explore that more?
Yes, I think it's definitely worth exploring with more complex stress distribution. But yeah, maybe having some fractal distribution, so random fractal distribution of initial stress, like sorry, what's the name? Sorry, I don't recall the name on top of my head right now. But what we are doing here is trying to just use the most simple case to, probably not a good word, to find the bug in what we have been doing this. So by introducing just the very simple shape here, I would say this is the simplest shape that we can have, so that we can have constant fracture energy throughout the entire fault plane that still have a very similar ruptures that will show the same scaling relation that people have been observed from natural earthquake. So of course, I think the next step will be having more complex initial stress distribution. And I also just want to confirm that, yes, we are trying to be very simple for the simplest way what we can do to have the model that shows that what we want to tell, that also have this scaling relation.
Okay, yeah, I guess before I turn it over to Massimo and other people, and Rachel, I see her has hand up, just point out that, for sure, anybody who's ever gone and looked at a fault, realizes that the geometric complexity, the real natural complexity of faults, and certainly no one would imagine that the stress state is really uniform. On the other hand, it can't be arbitrarily complicated either, because otherwise, some of the scaling laws that we observe between moment and length and things like that just, wouldn't work if there'd be a lot of outliers, I suspect, in terms of the source scaling relations that we often see for earthquakes. So there must be some happy medium in there between, incredible stress complexity and the way ruptures propagate. So it feels like there's more that could be done with your modeling.
Mm-hmm. I agree.
So Massimo, if you don't mind, I'm going to ask Rachel what she has to say, and then we'll come back to you. Rachel. Rachel, sorry, we don't hear you. Are you?
Hello, hang on.
Okay.
Sorry, I was just sorting out my internet connection here.
Yeah, don't worry. Well, plus, you were probably trying to anticipate Massimo having a nice long point. But
well, I was rather, yes, and I think
he's going to come after you.
Oh, okay, right. Yes, sorry. That was why I was trying to sort it out then rather than, anyway. So I guess I've got a number of things, and I hope this does turn into, you know, we keep the discussion going, because I don't want to just sort of say one thing. I mean, first of all, I really like what Chun and Greg and David and others are doing, because in some ways it's very like what Jim Rice and I were trying to do, nearly 20 years ago now, which is basically to sort of say, look, let's take the observations that we've got, which may be terrible and may be wrong, but if by some chance they happen to be right, what do they actually imply? And trying to find out what that range of things is, I think, is really important. And when I was doing the work back then, there was the sort of simplistic idea that if it was linear slip weakening and there wasn't anything else, then if you had a growing fracture energy with size, it meant you had a growing D sub C with size, which meant that basically, theoretically, the moment the earthquake started, you could tell how big it was going to be based on what the D sub C was. And we were basically just trying to, one of my main motivations for that work was actually to sort of say, hang on, this isn't the only explanation here. So the fact that there are other alternative explanations is very much in line with that, and I appreciate it. I'm continue to be concerned about the observations, as you know, from the seismology. But the other thing I'm sort of curious about here, you're basically going, now you're saying we're having a fixed area of high stress. So everything about the earthquake is being governed by the region which is stress, which sort of makes sense, because if there isn't any stress, there won't be an earthquake. But the work that we've been doing on small earthquakes has been showing how very variable they are and how not simple ruptures they are. But it's also, you know, for years has shown this large scale variability. And if anything, the spatial variability seems to be more constant than the temporal variability. So I'm wondering whether we would be better, you know, or the next thing to do perhaps is to explore models where instead of saying you have a region of a high stress and then a bigger region of a high stress and what have you, whether you vary the material properties instead, but try and keep the level of stress more constant, and what would that do? Okay, question for somebody.
Yeah, I completely agree with that. I just want to stress again that we are trying to find another M member. So the one M member will be fracture energy scaling, and on the other side, the completely opposite side will be, okay, fracture energy is a constant, and what can we do with it in the simplest way? And this is what we come up with. So it's by no means going to be accurate. It's just an M member case. And I agree that there's just too many things that can be, too many heterogeneities, maybe in geometrical or material property that could contribute to that. And another thing that I've been thinking about is whether is there still anything that we can explore for the scaling, or maybe the complexity is just way off. So we might as well do a just case study on each specific earthquake instead of trying to find a rule for all the earthquakes in the world. That's another thing that I've been thinking about. So I say it out.
Okay, yeah, Chun, you really fabulous. I'm going to give it to Massimo and then really encourage everyone to chime in, because yeah, obviously this was an interesting way to do this, to give this talk right after we had last week this incredibly nice focused discussion on this exact topic. So really nice talk, Chun-Yu, but let's hear what Massimo has to say.
Yeah, Chun-Yu, could you please show again the slide with the moment rate versus that you was just discussing before Rachel, before Chris? Yeah, the other one?
This one?
No, the other one, this one, okay.
So, sorry, this one, yes.
Here, if I understand well, now when you plot the moment rate, you are referring to the moment rate over the whole fault.
Yes.
Okay, so how this behavior change if you look at the slip velocity in each point of the fault? because I do believe that the slip velocity time history is much more related to the dynamic weakening and the stress behavior at individual point. And it should also relate it, and this also, in my opinion, affect the fact that the what you call the slip acceleration, no? Which affects the stress during the dynamic weakening, strongly also depends on geology, on the shear fabric evolution. So did you analyze the peak slip velocity instead of the envelope, the cumulative?
The peak velocity, the peak slip velocity, I didn't really
Sorry,
pay
not
too
the
much.
peak and the time history. Sorry, not the peak, the time history as well. Peak and
So the peak propagation velocity? Is that what you're saying? So you're breaking up.
No, sorry, I confused you with my last sentence. The idea is to see in each individual point on the fault plane, the slip velocity evolution with time as the rupture front is propagating. And if you see in the change in the slip velocity time series, this feature that you are pointing out with the moment rate, which is simply the envelope at a given distance, considering like a point source.
I would say that I didn't pay too much attention on that, but in the general idea that I get from looking at those data is that it accelerates to the sub-Rayleigh slip rate. Well, it's not dependent, but the slip rate kind of converges and then stops when it should stop. And for this case, then it's just that for the points closer to the, where's my mouse? Is it frozen?
I
think it's frozen.
No, we saw your mouse.
Oh, okay. Okay, now it moves. So for the points on the right, closer to the nucleation location, they didn't have too much time to continue slipping like a general crack-like rupture. So they stopped immediately after because its boundary tells it to stop. So it's not really dependent on the friction law anymore. It's more like a geometrical constraint on the slip rate history. So that's where the complexity come in. So it's not really going to be just solely explained by the friction law here.
Yeah, thank you.
So I hope that can answer the question, because the complexity coming from the geometry is more, it's dominating the behavior here rather than the friction.
Yeah, thanks.
Thank you.
Great. Other people would like to chime in generally or on the talk? I see there's something in the chat. Greg McClaskey, go ahead.
Yeah, so I like Georg's question, like where do the big numbers come from? Because people are getting these megajoule per square meter, big numbers, right? Where do they come from? I guess my thought is that I think Huey put it pretty well. If you've got 1 hertz data, and you're slipping at meter per second, you're only going to have a data point every meter of slip. And so it comes from the resolution. My guess is if you had a seismic network that was like sufficiently dense and sufficiently high frequency surrounding a smaller magnitude earthquake, you wouldn't get such big numbers. If people try to figure out what the breakdown energy is from one of these small earthquakes recorded in a deep mine, like in the South African study, my guess is it would not be megajoules per square meter, and it doesn't even slip a meter, right? So I think it's just a resolution thing.
Greg, I think that for one side, I agree with you, and the concept behind the FEAR project is exactly that. Try to record a minus fault underground with the density, with acoustic emission and other type of sensors to resolve this. But on the other side, I also feel obliged to take the part of Stefan Nielsen and the people working with high velocity friction experiments, because in those cases, you don't have any problem with resolution. When you sleep, the air surface similar to what you sleep in your large sample, a decrease of the shear stress, which is much faster. And even in that case, you might have multiple mechanisms, but they have a value of the fracture energy, breakdown work, whatever you want to call, which is the order of megajoule. So again, it could be a problem of resolution, but it could also be a problem of amplitudes of the phenomena and the energy in place. Because if we sleep 40 microns of sleep, and if we sleep 2 meters of sleep, we are involving completely different energies. And about the small number, I believe that Georg gave the answers at the beginning of the workshop before. So I think that the experiments on fracture mechanics for fracture energy that Georg was referring to on intact rocks of specific, they refer to another parameter. It is not, so perhaps we are calling with the same name two different parameters, but what Georg is referring to of about some joule or 10 joule for square meter, to me are different, because this, or at least this could be the fracture energy that we have where we have the coalescence of microcracks during sliding, but this is not what we observe at the scale of a propagating rupture front during an earthquake.
Greg, go ahead. I want to respond a little bit to that, but you go first.
Yeah, the rotary shear experiments that Stefan's talking about, they're very interesting. The thing that surprises me the most is that weakening, most but not all of that weakening that takes like a meter to accumulate, is happening while the slip velocity is increasing. It's taking so long to accelerate to meter per second slip rates that the weakening phase is getting drawn out. Whereas if you compare that to stuff that like Zev Rekas has done, where he's accelerating the sample much more rapidly, or you know, what you see when you have a dynamic rupture front, where it accelerates very quickly and then you have a slower deceleration phase, you see that weakening happens a lot. It takes a lot less slip for that weakening to occur. So I don't know, but my guess is that the way to reconcile the rotary shear estimates is that it's just not being accelerated quick enough.
I also had a similar comment, because, you know, one thing that's different about a real fault than Greg's experiments or the rotary is that they're much more geometrically complicated, right? And there's a wide zone within which things are happening, which could really increase the energy that's required to make it slip, let's say. But the rotary experiments are very similar to Greg's. They're done on, you know, basically, you know, flat, smooth surfaces. So if anything, they ought to be the same, not totally different. And I really think there's another set of things that are going on in those kind of experiments, where you're driving the system at these high velocities. And so you're not measuring fracture energy, you're just measuring all the heat that goes into, you know, making that surface slide. And, you know, the fundamental thing that's interesting about fracture energy, I suppose, is just that, you know, it really represents something that you could measure and ask questions about, you know, the energy budget of breakdown of energy release rates, and, you know, where does that energy go? It makes sense when you look at the equation. It's fundamentally interesting to ask, you know, how much of the energy goes into the fracture, various other things. And I think in a rotor, in a lot of, you know, shear experiments, you're measuring other things. You're measuring, you know, heat that's produced by slip that's not going to have anything to do with whether a fracture propagates, because by the time you generate a lot of frictional heat, the question of whether the fracture is going to propagate or not has already been answered.
Chris, I understand your and Greg reasoning, and honestly speaking, I am here defending the issue, not mine. But for instance, all people working with flash heating thermal pressurization like Nadia, Valer, that you have this weakening curve that are continuous decreasing, very similar to what is measured by high velocity friction experiments. So to me, I think that your concerns are correct. Okay, I think that thermal weakening is dominating where you have mostly frictional response. But at the beginning, you have a flash heating, which is evolution of properties, is not much different than what we are proposing here today for this sample. It's property of the contact evolution at the sperity sites. And you have this fast decrease due to flash heating. So I was referring exactly to this discussion when in the motivation of the workshop, I wrote that we have a lot of very good interpretive frameworks. If you are inside one interpretive framework, you are happy, but when you compare 2 or 3 of them, we have problems. And this is exactly the example.
Yeah, this is exactly the right slide to be on, Huey. Good for you. Yeah, okay. I'm going to pass on to somebody else who has comments, but yeah. Well, okay. Let's unmute and thank Huey for a fabulous talk. Really incredibly well delivered.
Well done, well done.
Beautiful background, and yeah, not an easy task to follow up on from what we did. So, thank you.